This is 3.4. We've already talked about finding zeros using synthetic division and long division, so we're going to take it to the next step because so far we've had kind of nicer polynomials and dealing with just real numbers. So let's talk about the fundamental theorem of algebra. So the fundamental theorem of algebra basically says if the polynomial of a certain degree n, then there is at least one zero in the complex system. Just as a reminder, every number is of the complex system. So because you have a real number here and then the imaginary aspect there, so that's called a complex number. So literally every number is of the complex system, but this fundamental theorem says there's at least one zero of whatever that degree is. And also, that goes hand in hand with that is the linear factorization theorem. So if a polynomial, p of x, with degree n, well, it has exactly n complex factors. So for instance, this is a general illustration, so whatever the n is, it could be to the 8th degree or to the 7th degree or whatever it is, that means that's how many factors it's going to be. Let's say 7. So if it's going to be a 7th degree, that's how many factors it will have of the complex nature. And of course, then that means that's how many zeros you're going to have. So these literally go hand in hand. Remember, a factor, if you know the factor, then you know the zero. If you know the zero, then you know the factor. So these literally go hand in hand with one another. So you know how many zeros there are, then that means you know how many factors there are in other complex zeros. So earlier we talked about at most, because we were talking about the real, like if it was a 7th degree term, then in the last lesson we said at most there's 7 zeros. Well, that's of the real numbers. But here this says that if it's 7th degree, that means there's 7 zeros of the complex system. All right, so let's look at 4 examples here. So 4 common problems, f of x equals x minus 2. Well, notice the exponent is a 1. So that literally means there's only one solution, one factor of the complex system. Well, if we set that equal to 0, we know x minus 2 is the factor, which means x equals 2. So that literally just means there's one 0. And again, in the complex, that would be 2 plus 0i. Okay, so every number could be written in the complex system. So that theorem holds true. So here we have x squared, which again, that means there's 2 complex zeros. At most, there's 2 real numbers, but there's there's exactly 2 complex. Well, this one actually factors nice to x minus 3, and when you solve this is going to be x equals, the factor, well, we already wrote the factor, x minus 3, so x equals 3 is the 0. So you could say this is literally repeated. Remember we talked about multiplicity? So this is repeated. So there are 2 zeros, they just happen to be repeated. So when you look at the graph, you're only going to see 1 0, but it literally is because you have x minus 3, and that multiplies together to be that trinomial. All right, let's look at the third example. Notice this is the 3rd degree, so I know there's going to be exactly 3 zeros of the complex system. Well, if I factor out the GCF, and then set this equal to 0. So I know x equals 0 is a 0, and then also x squared plus 4 is a 0, which basically means x equals 2i and negative 2i when you solve that. So notice there's 3 zeros of the complex system. And then here, the next one, x to the 4th. Here you have x to the 4th, and basically that means there's 4 zeros. That means x squared plus 1, x squared minus 1, that's how that factors. This one actually factors more, x plus 1, x minus 1. And then when you set all this equal to 0, you're going to get negative 1 here, you're going to get positive 1 there, and here you're going to get 1i and negative 1i. So you have 4 complex zeros. And again, the exponent tells you how many complex. Remember, at most, there's 2 real numbers. There's at least 4 zeros of the complex system. But remember the last chapter, the last section, we learned at most there's 4 real zeros. And that's true. So there's 4 complex numbers, but only 2 of them are actually of the real. So when you actually graph this, you're only going to see 2 of them that will actually cross the x line, the number line. All right, so let's talk about the rational zero test. So the rational zero test, basically, if you have some huge polynomial, so let me emphasize that, some huge polynomial, and you're going to look at basically the first and the last terms, the coefficients, p and q, and then all the possible zeros of this polynomial is listing all the factors of p divided by q. So notice on this illustration, we have p is the last, is -6, and q is the first one. So -6 over 1. So p divided by q is all the factors. Let me do it this way. Let me actually write all the factors of p. So that would be 1, 2, 3, and 6. Also, the factors of q are just 1. Okay, remember, this is your p right here. This is your q. Now, also, don't forget about the plus and minuses, because +1 and -6 are multiplied together to give you -6. So one could be positive, one could be negative. So this is literally plus or minus, plus or minus, plus or minus, plus or minus, plus or minus. So there's actually a lot of possible factors of that. And then p divided by q, you're just going to take all the possible p divided by q. Well, luckily q is only 1. So p divided by q is +1, +2, +3, and plus or minus 6. So those are all the possible. So there's actually 8 possible rational zeros. And what we're going to do is we're going to find all the possible rational zeros. We're going to find out, those are all the possible ones, but we want to find out which ones actually are the zeros for this polynomial. So if we just tried synthetic division, so if we tried 1, -3, 1, -3, and -6, and we literally just started trying these, because all of these are possible zeros. We don't know if they're, at most there's only 4, by the way. At most there's only 4. So these are all possible rational zeros. We just need to find out which ones will work. Well, let's try -1. Well, 1, bring down 1, and then multiply, add, multiply, add, multiply, add. So that would be -4, that would be 4, that would be 5, -5, -8, +8, and then I got 2. Well, when you make a video, you notice that sometimes you make a mistake. So instead of editing that, I'll just redo it. Sometimes it's good. It's a good lesson. Sometimes when it doesn't come out even, just go back and double check it. And I even wrote the coefficients wrong. So 1 and then -1, +1, -3, -6. All right. And then we're going to bring that number down. Multiply, add, multiply, add, multiply, add. So that would be -2, 2, 3, -3, -6, +6, 0. So -1 is, so we're testing to see which ones are zeros. And let's try 2. Again, I'm just trying these numbers here. So 1 times, bring down 1, and then multiply, add, multiply, add, multiply, add. So that would be 2, 0, 0, 3, 6, and 0. So x equals 2 is also a 0. And then notice what we can do after that. What I have so far is x +1 is a factor, x -2 is a factor, and then this remains x squared +3. And that is my polynomial. So let's call that f of x here. So I basically factored this big long polynomial, I factored it to that. And if I wanted to, I could set these all equal to 0 and find all my zeros, okay? All my zeros. But in this specific problem, I'm only finding the rational zeros. This number right here would not give me a rational number, okay? So set that equal to 0 and solve it. It's not that big a deal, but it's not rational. And if I specifically ask for rational zeros, then these two are the only rational zeros. And by the way, if you push graph, if you type that into your calculator and push graph, you would be able to see that it crosses at these 2 spots, nice and easy. and these two would be decimal answers. Okay, actually they wouldn't even cross at 0 because you'd have an imaginary number there, but you could still find those numbers because there are 4 complex rational zeros, or 4 complex zeros, and 2 of them are rational. All right, let's look at another illustration here. So here, notice f of x equals 2x cubed plus 3x squared minus 8x plus 3. So notice automatically x equals 3. That means there's 3 complex zeros. So if we did p divided by q, so p divided by q. So p is positive 1, positive 3, all the factors. Q is positive 1, positive 2. And then p divided by q is 1 divided by 1, which is 1. 1 divided by 2, which is 1/2. 3 divided by 1, which is 3. And then 3 divided by 2. And these are all plus minus. And these are all the possible rational roots. And so if we start using synthetic, we can start narrowing it down to find out which ones actually are 0. So 2, 3, -8, 3. And I'm going to choose 1. So I'm going to bring 2 down. So 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. That's -3. That's -3, and that's 0. Yes, x equals 1 is a 0. Which means x minus 1 is a factor. And what I have remaining is 2x squared plus 5x minus 3. And then you could solve it by using the quad or just factor. And it does factor. So notice this polynomial that I began with factors to this. And I do want to be clear on this. This is the 0 x equals 1. This is the 0 x equals 1/2. And this is the 0 x equals -3. I do want to caution you real quick. If you use your calculator to begin with it and you found these 3 zeros to begin with, I want to caution you not to do this. X minus 1, x minus 1/2, and x plus 3. And I've seen the students do this and they think that's the factor of it. The problem is when you do that, if you FOIL those 3 parentheses, it does not equal the polynomial to begin with because of this guy. Okay, so anytime you have a fraction here, you got to remember, how did that become a fraction? And so like 2x minus 1 equals 0. If I solve that, you're going to end up getting 1/2. So anytime you get a 1/2 or a fraction, you got to kind of go backwards. Like, how did you solve for that 0? And so this is not correct here. It's actually 2x minus 1 to be able to do that. And again, if you FOIL this, notice the first term is 2, so you should have a 2 in one of those first terms to be able to do that. All right, just real quick, a conjugate pair. You definitely need to know this. Every complex 0 has a pair. So like 3i and -3i. So let's look at this last example. Find a 4th degree polynomial with these 3 zeros. That's the only 3 zeros I'm giving you, even though it's a 4th degree. Well, again, notice 3i. If I give you 3i, that automatically means -3i is also a 0. You definitely need to know that. So x -1 is a 0. That means x plus 1, x plus 1. These are all factors. And then x minus 3i and x plus 3i. And then all you have to do is FOIL that out. Notice we had multiplied all that out. And then notice the only thing that we haven't done yet is that. And so we just need to make sure the leading coefficient is -2. So I'm going to basically multiply everything by -2. So we found a 4th degree polynomial with these zeros, and it has a leading coefficient of -2. That's 3.4 zeros of a polynomial.